Doppler effect is an interference pattern caused by the sound source moving or the person listening to the source is moving. It also applies to echoes off a moving object. You're all familiar with it with the meow sound when an object moves really fast. There is an audible change in wavelength. The effect becomes more pronounced as the vehicle moves faster, so it wasn't really noticed before trains. I mean, face it, no one ever rode a horse so fast that it went as it went by anyone. George Stephenson was an Englishman who made the first passenger rail with his aptly named Killingworth locomotive. In 1829, his better locomotive, called the Rocket, ran over and killed Member of Parliament William Huskinson, and he became the first person in history to be killed by a train. Doppler had noticed the wheeum sound when something quickly goes by with you, and he did the math to explain why this new sound effect was so, and he was the first one to explain this new sound effect with mathematics. He did it by towing trumpet players with perfect pitch up and down train tracks at different speeds till he got the math to agree. And he was smart enough to realize that it not only applies to sound wave and waves on water, it would apply to light waves, and that if a star was moving quickly towards Earth, it should shift to the blue end of the spectrum, and if it was moving away, it would turn red, as in red being like the lower pitches. So Doppler was well ahead of his time, and he managed to avoid getting run over by a train. How does the Doppler effect work? First of all, every little boy knows how to do it. There's not a boy on the planet that doesn't go meow. And that onomatopoeia, believe it or not, is done by males like 80% more than girls. So males have such a poor vocabulary, the best thing we can do is go like, there's Star Wars and Luke, I am your father. And girls go, I saw this movie about a boy who had his father's lightsaber. But us boys, we just tend to go like, and do noises like that. And then women want men to write them poems. And I think the girls have the vocabulary. They should be the ones writing poems to the men. So, I want you to watch these two videos because this is the best way to learn the Doppler effect. But let's take a look at what it means in school. First of all, get this through your head. If you're going la, the flapping of your vocal cords has nothing to do with the speed you're moving. If I take the devil's flute, the recorder, and blow it, the fact that I am revolving around the Earth and the Earth is revolving around the Sun and the Sun is revolving around the galaxy does not affect the rate the flute blows at. The frequency is fixed. Okay? It's like a beaver slapping his tail. Whatever is creating the noise, that pulsation is fixed. That's the key. Don't play with the frequency. Now, the object begins to move. As it's slapping the air and making the sound waves, as it begins to move forward, it begins to affect the wavelength. So if you keep that in mind, that the frequency is causing the waves, that the frequency does not change because you move. You never start to walk and have your guitar change its tuning. It stays fixed. So here's what happens. The speaker is going pulse, 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 and these waves are going off into the distance. And they maintain a fixed spacing because you're like a beaver going clap, clap, clap on the water and the waves move forward. Now, what happens if between pulses you suddenly stepped forward? You went and you jumped forward and then you did the next pulse. You maintain your pulse rate, but you shorten the wavelength because you deliberately moved forward between the pulses. Now, the time between pulses is called the period. So between your clappings of your hands, so you're doing this on water, going on the water. The time you have to move is the time between the pulses. So you have one period to move forward before the next wave is emitted. This means you can move forward a distance equal to your speed, not the speed of the wave, the speed of the source moving forward. So if this is your car horn and you are playing 440 hertz horn, me, and you are moving at 30 meters a second, then between each one of those pulses, what is 440 hertz in time? It's 1/440th of a second. Your car will move forward a little bit and shorten the wave. So the wave that the car started with, whatever the wavelength is, which we would have to calculate, shortens by the speed with which your car moves forward times that single period. And we call this shortened wavelength a lambda prime, meaning it's the after effect of it, the final wavelength. Now, for sound, we need to convert this wavelength to frequencies, and we will do this with the universal wave equation. You will solve for lambda and substitute it into this equation above. For now, we can leave the formula like this. Measuring wavelength is common for light and waves in water. But for sound, we typically use frequency. So you're going to have to get used to doing both. If you do sound, frequency is more commonly referred to. Frequency is referred to with radio waves, but light and water waves are always measured in wavelength. It's not hard to do the two of them together. Middle A on the piano is 440 hertz. As a wavelength, this would be calculated from the universal wave equation. You would take the speed of sound equals f lambda and solve for lambda. In air, at room temperature, you will get a speed of sound of about 345 meters per second. Solving for lambda, you get about 80 centimeters, 0.78 meters. Now, what would you rather call middle A on the piano? 440 hertz, or say, hey, play me a 0.78 meter? They're the same, just one sounds weird. How come we adopted sound is in hertz, but light we kept wavelength? Because the wavelength will change when the temperature changes. When you play middle A and you get la, it doesn't matter if the day got warmer or colder, the sound coming out of your stereo is still going to be playing 440 pulsations every second. The frequency won't change coming out of the loudspeaker. However, if the day is warmer or colder, the wavelength in the air will change. So the frequency again is the constant. The wavelength varies. With light, it's not really an issue. Light speed through the air isn't really bothered by temperature. Let's take a look at the equation now. We have to be careful. We have two different speeds. The speed of the source and the speed of sound. It's common to use a script, a cursive V. So to avoid having these two large words, and we can't use small subscripts. I mean, look at it. The first three letters are identical, so we can't use VS and VS. So capital V is often used in the textbooks, but that's a bugger to write by hand and make sure you know it. So instead of writing the speed of the source like this, I'm using a script V and I'm putting it in red so you understand that's the speed of the moving object. and then the speed of sound, according to the universal wave equation, I will use a capital black V to make it easier to see. What we want to do now is knock out the two lambdas, because we cannot hear wavelength. We cannot see the wavelength of sound, but we can hear pitches. So all of you can go, yeah, I heard that. What wavelength is it? I can't see air pulsations. My ear hears frequency. So if we rearrange this formula to knock out lambda, then we can do two substitutions on it, like this. I left the V in black because it doesn't change. That's the speed of sound. So if we replace these, we get this substitution. Now the period is also 1 over f. So we're going to get 3 substitutions here. You need to try this on your own. We replace lambda with v over f. We replace lambda prime with v over f primed, and the period is the same thing as 1 over f. So we are going to simultaneously knock out 1, 2, 3 terms and see if we can get nothing but frequency. I want you to try it on your own. It will mean nothing to you watching it happen. So I'm going to pause. Do 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 dun do 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 do. Okay, ready for the rearrangement of the century? There it is. There it is. Look at that. Look at the beautiful equation. It is so lovely looking. There's the substitutions. You can pause and stare at it and be mystified by my color-coded rearrangement. Isn't that beautiful? F primed is the speed of sound over the difference between the speed of sound and the vehicle's speed, and that's the multiplier that will cause the frequency to change and summon my children and the dogs back to my home. Does this formula seem reasonable? Let's check. It basically looks like y equals mx. There is an answer from an original number that's got a multiplier on it. The only way for frequency to wind up as frequency is that this multiplier has no units, and speed over speed has no units. So this is a dimensionless coefficient. That makes sense. The formula looks correct algebraically. Let's check the physics of the equation. We know intuitively if the source of sound does not move, then there is no frequency change. If you're sitting still, a horn just goes eh. If the car moves, then you hear meow. So F primed, the after the Doppler shift frequency, and the original frequency will be identical if the source doesn't move. If I put 0 in here for the speed of the moving object, then this equation just turns to v over v and generates exactly that. F primed equals f. So we check a value that is very defining of it, and it's working. This formula predicts no frequency change if there is no movement to the source, so it works according to the rules we understand. But something funny happens. If the sound source moves at the speed of sound itself, that is, the object that's moving, like the train blowing its horn, equals the speed of sound, a Mach 1 train, then the term v over this difference in speed becomes undefined or infinite. This means the Doppler frequency goes zooming to infinity if you reach this speed of sound. WTF? What the physics is going on here? We'll look at that later, but the formula looks sound, so we'll tackle some examples. We're going to do a computation with this formula, give it a trial run, and see how it works. So a train horn blows at 900 hertz, and yes, I looked it up. That's the common pitch of most train horns in North America. The train is moving at 40 kilometers an hour, a totally possible speed for the train to move on a 20-degree centigrade day. Calculate the frequency people hear in front of the train and behind it. You'll see it's really easy to do both. The first thing we have to do is calculate the speed of sound. We use the formula 330 meters a second plus 0.6 t, and we get 342 meters per second on this day. The speed was given to you in kilometers per hour. It must be in meters per second for a formula to work. Now that we've set up our variables, we are simply going to take the formula, put in the speed of sound at two locations, and subtract the speed of the object. Multiply it by the initial frequency, and we get 929.9 hertz is the new sound. What if it's moving away? Well, moving away from you would be negative on the speed. And a double negative becomes a plus. You multiply that by 900, and you get 871. So the people to the rear of the train hear a lower pitch than the people that are in front of the train. And if you look at the spread, there's an equal number of hertz above and below the stated frequency. So the one went up by 29.9 and the other one went down by the same. I'm going to show you a little calculator trick to save time on formulas that have these terms underneath. Instead of doing this, trying to take 342 and then you divide by 342 minus 11 and forget brackets, and you wind up generating some bizarre little number. The easiest thing to do when there's multiple terms in the bottom, do those first. Watch, do 342 minus 11. That's what it equals. Now I can put it on the bottom of the fraction by this key. And now it's down below, and I can multiply by 900 and multiply by the 342. So if you have a large denominator, the easiest thing to do is finish up everything you're doing in the denominator first, get it all done, and then just flip it with your flippy key. It'll either say 1 over x or x to the minus 1, and it saves quite a bit of time and lowers the error rate. Moving on. Now, how much shorter did those waves get that we just heard? When the frequency changes, right, and it didn't really change, the horn still vibrates at the same rate, but the receiving person gets more waves per second. So I'm kind of curious what happened to the wavelength. Well, what we can do then is solve for the wavelength as it originally was and solve for the wavelength as it is now. Okay, now be careful. The universal wave equation does not use the vehicle speed. It uses the speed of sound. So make sure you understand what the equation is talking about. This equation is talking about a moving wave. That V has nothing to do with the vehicle speed. It's the speed of the wave. If I take the speed of sound, divide it by 900 hertz, we get the original wave would have a wavelength of 0.38 meters between sound pulses. I put in the new frequency. Now I rounded on screen to save space, but I used the exact number 929.9. I get 0.367. So the wave didn't shrink very much, and that makes sense. There wasn't much wave shrinkage because the train is only moving 11 meters a second compared to the 342 meters a second that the sound is moving. So even though the train is moving quick enough to kill you 10 times over since Sunday, it's not very fast compared to the speed of the waves. So it couldn't shrink the wave sound very much. Well, let's see if we can find another tactic for this. Recall the diagram from earlier. Every time a pulse is emitted, there's a time gap, a period between one wave pulse and the next, giving the vehicle time to move forward somewhat. And the time the train has to move forward is exactly one period between the waves. Period is the same as the reciprocal of frequency. The true frequency of the horn was 900 hertz because that is the real physical vibration of the mechanism in the horn. It's not the second frequency, that is the perceived frequency. The real horn is what we're talking about. The horn made a noise every 0.001 seconds. You invert the frequency, and that means the little mechanism in the horn that's going back and forth, making sound, there was 0.001 seconds between subsequent waves of the sound. So the train has 0.001 seconds to sneakily advance before the horn makes another sound. So the question is, how far forward did the train go when it had 0.001 seconds to advance before the horn slapped the air again and made the second wave? Well, that's real simple. D is equal to V times T. I use capital T because we're talking about period. This means the train was able to advance 0.011 meters. Not very far at all, like literally 1 centimeter forward is all it got between 900 pulses a second. That makes perfectly good sense. When we calculate this 0.011 meters is exactly the gap between lambda and lambda prime, with, of course, the fact that I didn't carry these digits out. 1 over 900 is 0.001 repeating for eternity. So it works out fine. What we can do by thought process generates the same result as the universal wave equation. The wavelength shrank because the train had a brief moment of time to sneak forward a little bit before the next pulse. The math is grade school. The understanding takes a while to really get your head around this. And the number one mistake we see in here, I see two year after year, thinking that the speed in the universal wave equation could somehow turn into the train speed. The speed in this equation is definitely the speed of the train. The second mistake I see is people not being sure which of the frequencies are we using in a new calculation. Well, the real horn itself slapped the air 900 times a second. So the number one errors are conceptual errors to confuse the originating source of the sound, the initial frequency, and to confuse the speed of sound with the speed of the object. That's the hard part. Now there's something really nifty we can do. Most of you know when a submarine goes ping, ping, and it comes back, that they're timing the pings. But the ping can go out and go ping, ping, and come back higher, or the ping can go out ping, pong, and it comes back lower. The pitch will change. And even though it's an echo, the echo will still return with the vehicle speed added or subtracted to it. So we can use an echo from an object to tell how fast it's moving. What we have to do is rearrange the Doppler equation to solve for the red V, the vehicle speed. Can you do that? You can pause the video. Doom, 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 doom. Doom, 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 doom. Do 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 doom 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 do 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 doom 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 boom. Okay, let's see what happens when we rearrange. I move the entire denominator to the other side, because remember this is all multiplied together. I'm left with this. Then I get rid of the f that's multiplied. It shows up on this side. And now we got to get rid of this guy here. So one more rearrangement and there it is. And of course, you're probably going to want to move it like flip left to right. And this again seems to be a reasonable looking formula. Let's pause and take a look at it. The vehicle speed is going to be related to the speed of sound somehow and the ratio of the frequency pitch. So that seems like, it's a little bit tough to think about, but it seems like it should be reasonable. It's related to the speed of sound and the frequency change. So everything in here, it didn't show up like air temperature, density, nothing else showed up. It seems to be reasonable. We plug in our numbers and you'll get 24.5 meters a second, which is getting really fast for a sub. That's getting up there. And so my gut reaction would be that's a torpedo coming at you. That's almost highway speed underwater. There's only a few subs that can do that we know of. So that's booking. That's moving. Oddly enough, while submarines have trouble going that speed, a swordfish can do it. So now you've just used Doppler sonar. And that's how we can tell the speed of things. This also works in your bloodstream. If there are things zipping through your blood, we can bounce the Doppler ultrasound off, not only image the blood, but we can get the speed. This is how Doppler radar works. We can bounce a radar wave off a cloud, and it comes back. And if it comes back faster on one side and negative speed on the other, then the cloud is rotating. So the Doppler, when you hear Doppler radar, Doppler ultrasound, Doppler sonar, we're accounting for the fact that we can get the pitch change and get speed, not just distance to the target. Doppler originally came up with the formula for use in studying the stars. He proposed that the speed of a moving star would shift the wavelength of the light. Later, he applied it to sound. With light, we always refer to the wavelength, not frequency. So of the two variations of Doppler's equation, the left version is more commonly used in physics than the version on the right side when we're dealing with light. And the left version will play a very significant role in grade 12 optics with diffraction. You'll always be using wavelength, not frequency. Now we're going to rearrange the formula on the left by pulling off a substitution. We need to get period out of there, because period and frequency are the same thing, just in versions of each other. So we want to knock the period out of there to make a usable equation to talk about wavelength. Taking the universal wave equation, we can phrase it as f lambda or lambda over t, because f and t are reciprocals of each other. This gives us period as lambda over the speed of sound or speed of light. It's the wave speed, not the speed of the moving object. So we'll knock out period and replace it with that expression. And we get this. We'll move on to the next slide where we start to rearrange this and group some terms so we can make a solution. This is where we were on the last slide. And now we're going to group like this. This grouping of a common multiplier like lambda and putting everything else in brackets with that 1 minus v source over v sound, in the case of its sound, is really common in physics. We do this all the time. And then you can sort of see that the lambda prime and the lambda are related to each other by some multiplier that has to do with the speed of the wave. In optics, this wave speed is called light speed, and since it never varies, they gave it the logical letter c for the speed of light. Because Germans. And there she be, the Doppler shift formula when you're talking about moving light. Doesn't seem like a big deal, but this little formula changed the world in ways you cannot imagine. What this predicts is, the faster your vehicle, that red speed is, you will start to see light change color. It will shift to the blue end of the spectrum or the low end. So the neon of sound in terms of light would be blue-red. It would go like that. But you're really going to have to be moving to have this effect happen. Oh, look at all of the pictures. This looks like it could be complicated. This is grade 9 through grade 12, something you're going to do. In grade 9, we allowed you to set fire to certain chemicals in a flame called a flame test. And you saw that sodium gave out a distinct yellow color. You've probably heard of the spectrum and that a prism would give you a spectrum. Now, depending on who you had as a teacher, the teacher might have had a prism or a spectrograph to hold up to a light, and you would have seen that many of the lights in the room did not emit a rainbow of colors, but they only emitted certain highly specific colors. This is called an emission spectrum. You look at sodium and you see yellow light. The emission spectrum breaks it down into the exact colors of yellow that went in to compose it. It's similar to a device called a colorimeter that you see at hardware stores. You can bring in an old paint swatch and the colorimeter will decompose the mixed paint and tell you what pigments to buy to mix to make another one. The reason atoms have very specific emission spectrums is due to the electrons. They jump up and down between orbits, and since the orbits are fixed or quantized, you have orbit 1, orbit 2, orbit 3, the electrons don't spiral from one orbit to another like planets could do. They literally just snap from one orbit to the next with no time delay in between. So they burst out very specific colors of light for every possible transition from one orbit to another. This will become a major feature in later chemistry and physics. So hydrogen has tons and tons of transition lines just with the single electron, how many jumps it can do. Only a few of these lines are in the visible spectrum. The absorption spectrums occur when, say, hydrogen gas gets between us and a star. Then instead of emitting those colors, the gas will suck them up. So it's like the opposite. This is emitting, this is swallowing. So we're going to look at what happens when a light source moves really quickly, and you think of these emission spectrums, pretend they're keys on a piano. Each of them is a color-coded key, and we're going to get a neon with the light. The first person to pull this off was in 1868. William Huggins actually used Doppler's equation and successfully measured a shift in hydrogen light from a star. And that was pretty impressive for 1868, and we're going to take a look. Now, visible light, just like sound, there are frequencies you can't hear. In the visible range, the range of light sizes goes from 390. The range of light is 380 nanometers to about 800 nanometers. It's common to put blue on the left. I prefer to have it the other way because the red would be like the low notes on the piano and the blue notes would be the high notes. But it's pretty common for them to put the blue on the left, but it makes it go opposite the musical instruments. These numbers up here are called angstroms. That just means power to the minus 10. It's just another metric prefix that never caught on. 380 nanometers is getting so purple you can't see it, and it turns into ultraviolet. 800 nanometers and beyond is getting so red you cease to see it, and only animals that can see in infrared or soldiers can see that color. So let's take a look at the 4 colored lines that you could see in hydrogen with the naked eye. You put hydrogen through a spectrograph, you will see these 4 colors in the rainbow. And we're going to pick the 410 nanometer one, which is going to be the shortest one on the list, making it way down here, about this one. That's the 410, okay? If I take my formula from the last page, I put in 410 nanometers, we find it shifts to 409.49. That is literally narrower than the width of this color band. So for Huggins to see this would have needed to be a very advanced spectrograph to possibly be able to tell what was 0.5 of a nanometer. And think about it. This drawing here is going through 400. So to see a difference of 0.5, it wouldn't be visible on this. You'd need a really good machine to see that shift. What happens if we were on a ship and we are traveling really fast? Like we actually start approaching the speed of light, what would happen? So let's say we're going to a peaceful yellow star and it has a wavelength of about 500 nanometers. That would put it in the yellow category, pretty close to our sun. Your ship is traveling at 3/4 c. That means 3/4 the speed of light. So you would take 3/4, multiply it by 3 times 10 to the 8th. What wavelength will the star's light be shifted to? And in this case, it will be a blue shift because you're heading towards the star, not away from it. So we take the formula, we put in the 500 nanometers, and we put in 3/4 of the speed of light in the denominator, in the numerator. We put in 3/4 the speed of light on the top of the fraction, the speed of light on the bottom, and unfortunately the wavelength shift brings it to 125 nanometers. This has gone from yellow not to blue, not to really blue, not to ultraviolet A, not to ultraviolet B, but it's gone all the way to ultraviolet C. That wavelength of light is so far into the ultraviolet, it's used to kill bacteria. This would be the kind of thing used in people that have UV sterilization in a well. It would blister paint. Fortunately, it's still in the ultraviolet spectrum, so your ship with the metal hull, at worst, you're going to get the paint peeling off, and it's possible for ultraviolet at this wavelength to begin to ionize. So the front of the ship might start picking up electric charges. If you go much faster, the shift could put you into the X-ray band, and you literally can fly fast enough to be X-rayed to death with this wavelength shift. So that is something they never really cover in science fiction movies. As you approach the speed of light, you begin to slam into the waves of light from a star to the point you can eventually turn peaceful visible light into deadly gamma rays as you approach it really quick. This also allows us to think of the absurd. You could run away from a sunburn. If you ran fast enough away from ultraviolet light, you would shift it downwards until you turned it red light. So out of curiosity, let's suppose you're near a blue star of wavelength 300 nanometers. So that star would look jet black to you. You wouldn't see it, but man, oh man, would you get a sunburn if you were anywhere near it with that kind of wavelength. So how fast would you have to run to take the dangerous blue light and turn it to harmless red light? Well, let's see. We would start with this formula, and we're going to try to solve for a speed that would generate the wavelengths we want. First rearrangement like this, and then I rearrange the terms again, and then one more step, and we put it all together, and we get about 1/6 the speed of light. So if you were for some reason able to run really fast, you could theoretically run away from a sunburn. You could go, yeah, I was running so fast that the sun's light turned red and didn't burn me. But seriously, running at 1/6 of the speed of light is probably even past what this guy can pull off. I mean, he'd really chafe if he tried that. So why is this redshift and blue shift important. In 1939, Edwin Hubble discovered that every star was redshifted. So remember, it was like 60 years earlier that the redshift was discovered, but then he started cataloging the sky and noticed every single star was redshifted. This means that every star in the sky was moving away from us, and the further the stars were away from us, the faster they were receding. This was direct evidence of the Big Bang. The part that's not well explained and can cause mental confusion is how can you tell a red star that is standing still from a blue star running away so fast it looks red? Simple. It's that emission spectrum or absorption spectrum of an element in the star. It's like a unique barcode. You expect the pattern of black lines to be in specific color ranges. If the lines are redshifted, you would see the pattern you expected, but too far over in the red. This would be like recognizing a song, but you're surprised when it's sung an octave lower than your expectation. This is how we tell the difference between a stationary red star from a rapidly receding blue star. And it's proof of the Big Bang, one of many pieces of proof of the Big Bang. But this also is an effect that is strong enough to be seen by the naked eye now with black holes. Physics has a great history of prediction. Because the strong mathematical foundation, more than any of the other science, it makes predictions that have a solid, quantifiable truth. It can make predictions that even seem absurd to the person who made the equation, but later turned out to be true. With Newton's law, the 1 over r squared term predicts that as you get closer to an object, the gravity will grow. Well, you can't get closer to an object than the surface. So in this universe, we have the constant g, and we have the two masses that are attracting themselves. If you were on the surface of the Earth and we squeezed it smaller and smaller and smaller, then you would be closer to the center of mass. It's not about you tunneling into the Earth. If you were at the center of the Earth, gravity would be zero because there would be a tug of war in all directions on you. So if you could somehow squeeze the Earth, you would get progressively closer to the center of mass. And for example, if I say the Earth has a radius of 2, then the approximate force of gravity would be 0.25. You have to multiply it by all this stuff here, but we're just looking at the comparison. If I shrank the Earth from this arbitrary diameter or radius of 2 to 0.2, the gravity would grow, right, by 100 times because I shrank it 10 times. Well, you keep doing that and you keep putting a smaller and smaller radius in that formula, it eventually says gravity should reach infinity when the size is 0. Newton's law of gravity from the 1600s predicted the existence of black holes, but at the time they just said it was just a mathematical oddity of the formula. They didn't really believe such things could exist, and now we have pictures of them. When Einstein came along, we really took interest in black holes and predicted their existence. This was a scientist in the 1970s who ran a big supercomputer and got calculations done, and then he hand plotted these on paper. This is not computer graphics. He got the data and he plotted every one of these points on here, predicting what a black hole would look like. Well, a couple years ago, the movie Interstellar, Christopher Nolan invested enough money to put a supercomputer to work, and they generated this simulation of a black hole. This is not CGI in the sense that, oh, it's our fantasy of what it would look like. This was done with the physicist Kip Thorne, and it was the most accurate simulation of a black hole at the time. So accurate, in fact, they used it to do research with. So Hollywood was able to pay for something NASA couldn't afford, and the simulation is so accurate, the scientist Kip Thorne actually got scientific papers out of it. What happens when we actually finally saw a black hole? This was just a couple of years ago in 2019. That is the first picture of a black hole ever taken as a photograph. And since then, they've improved the technique, and this is the picture of the black hole. And what you are seeing is a low-quality version of that. Turns out the black hole is exactly as predicted by the Kip Thorne. The part that's missing is this little thing here called a photon ring. There's not enough resolution here to see it. To give you an idea of the scale of the black hole, I put the Sun to Pluto in there to show you the size of it. And why am I showing you this with Doppler shift? Because as you come towards a person, you blue shift. As you recede, you red shift. This side of the black hole is coming at us, and the light has been shifted towards the blue end of the spectrum. Now, it was red originally, so it didn't blue shift all the way to blue. It just got halfway through the spectrum. But this is rotating towards us, and the darker red is rotating away. This is called Doppler beaming. It's a combination of Einstein's law and the Doppler effect, but it's visible Doppler effect on light. You would actually see a change in color on the black hole from one side to the other, depending on if it was rotating towards you or away from you. You can read this slide, but basically this side of the black hole, the debris around it is coming towards us. This side it's going away, and you get a brightening towards the yellow and a darkening towards the red. Why you see this disk over top and underneath has to do with the black hole's gravity. The black hole has a ring like Saturn of debris going around it. This side of the ring of debris, if it's going away from us, it red shifts. The far side of the debris, as it comes towards Earth, it blue shifts. Light that tries to escape the back of the black hole, some of it is caught by the black hole's gravity, and it's slingshot around the black hole, and that makes you see the ring bent up and bent down behind. And that's what you're seeing. You're seeing a mirror image of the back side of the ring that went behind the black hole, and some of the light got twisted up and some of the light got twisted down. So there